chapter 11 here for just a few minutes before we're done. Just give me a second. We're going to talk about sort of modern atomic theory. Really what we're going to be talking about in this chapter. Electrons, where they're as electrons sort of move from one energy level to the next, that requires a certain amount of energy to do so. And as they come either up in energy or down in energy, how that energy is either absorbed or released in an atom. So from Rutherford basically described, as we talked about at the beginning here, that an atom basically has that dense positive core, which is our nucleus, where our protons and our neutrons are housed. Nucleuses are very small compared to the size of the atom. And it's really the electrons that are on the outside flying around in that empty space. And they're really involved in most things that happen in normal chemical reactions, because if you think about it, electrons are flying on the outside. So when atoms come together, it's obviously the electrons that sort of come in contact with each other sort of first. So a lot of the idea of electrons and sort of how they transfer from one energy level to the next, which is sort of what we're going to relate most of what we talk about here in this chapter to. A lot of it was done, or a lot of beginning part of it was done by Planck. He did a lot of work with radiation, and he came up with sort of the idea that energy can be released in only these sort of certain definite amounts of energy. They're sometimes referred to as packets of energy, which is a quanta of energy. And in the case of what we'll sort of relate it to, as electrons sort of move from one energy level to the next, so as the electron goes from a lower energy level to a higher energy level, it needs to gain a certain amount of energy, right, to allow it to, that's an endothermic process. Energy's got to come in to do that. And if we have electrons that are in higher energy levels, and as they drop back down to lower energy levels, they actually have to release a certain amount of energy to do that, to allow them to go from one energy level to the next. And that's actually an exothermic sort of process. The way the energy is either absorbed or released a lot of times is through radiation, and really through in the form of waves, or a photon of light, which is basically a wave. So a lot of what we talk about has to do with waves, and the idea of sort of quantized energy, we'll see, I think, a picture of it a little bit later as well in this chapter, but just really quickly, is sort of like the idea of stairs. And as we walk stairs, right, we usually have enough energy to get ourselves to this step or that step, right, either going up or down, whichever way we're going. We don't usually start up a step and go, I want to just kind of rest like halfway up the step, because we'll fall. And that's sort of the idea of sort of quantized energy. The idea is this: as electrons transition from one energy level to the next, they will either gain enough energy to get themselves completely to that energy level, or they will lose enough energy to drop down to another energy level. They will never find themselves in between energy levels. And that's the idea of sort of quantized energy. You have enough energy to fully make that transition from one to the next. Just like when people walk stairs, right? Some people can do one step at a time, two steps at a time, right? They have enough energy to do two at a time, three. Nobody does three or four at a time, but maybe. But, same thing with electrons. They gain and lose energy enough to fully transition from one energy level to the next. And as they're doing this transition, it really is sort of waves that come off or absorbed that really pack some energy associated with it. And a wave is basically a vibrating disturbance in which energy is transmitted. The bird there has the right idea at the beach, right? But as he's coming through, right, the wave is coming through, he's actually not moving, right? He's just kind of coming up and down and bobbing. And obviously, if you ever went swimming in the ocean and got hit by a wave, it has a lot of energy associated with it as it's dragging you underneath. And that's sort of how energy is sort of moved as electrons sort of transfer from one energy level to the next. And it does bring up the idea of the conservation of energy that we talked about, I think, in the previous chapter. if there's a certain amount of energy requiring for those electrons to go, say, from the first energy level to like the third energy level, if it needed to come back down from the third energy level to the first, it would have to give off the same amount of energy to require that transition to occur. So we have that sort of conservation of energy that occurs as things transition. Some important parts of a wave, and we'll talk more about it here in this chapter. But first off is the wavelength, which is sometimes abbreviated with the lambda symbol. So if you got a wave kind of moving, that is like between two peaks, right? Or troughs, which would be the bottom, is the wavelength. Typically, wavelengths are given in meters, centimeters, and nanometers. Reminder that there are 100 centimeters in a meter, and in 1 nanometer, there are 10 to the minus 9 meters. So those are common units that are used in conversions. Frequency, although people call it V, it's new, is the number of waves that pass through a particular point in 1 second. It is oftentimes measured in hertz, like when you dial your radio to a certain frequency, like 95.5 megahertz, right? So mega is sometimes used a lot with frequency. Mega is 10 to the 6, right? Hertz is also a reciprocal second. So that is also a common unit that is used. 1 over S, a reciprocal second. So once again, a hertz is the same as a 1 over second. The amplitude is from the midpoint to the peak there of the wave. So that would be like our amplitude right there. And we can actually calculate the speed of a wave by taking the wavelength times the frequency. And if we just look at units, the wavelength is typically in meters. The frequency is 1 over seconds. So when we multiply it, it is meters per second, which is a very common sort of speed of waves that we talk about, or velocity of the waves, and how they travel are common units that we end up with. Any questions on that there? All right. To chapter 11, and we started talking about, and what we're really talking about in this chapter here is electrons, basically, electron configuration, sort of where they are. And really the idea of what we'll talk about here is electrons, as they sort of transition from one energy level to the next. As we talked a little bit about last time, it does require obviously a certain amount of energy to do those transitions, regardless of sort of which way you're going. If you're going sort of lower energy to higher energy, they need to absorb energy, which is an endothermic type process. Energy needs to be absorbed by the atom to excite those electrons. Kind of like what you did when you did flame tests the other week, and you stuck the thing into the flame. Obviously, you excited all the electrons with all that energy. And what will eventually happen as well, though, is things in chemistry do like to be in a lower state of energy. So the electron will sort of relax back down to lower energy states. So they'll go from higher energy states to lower energy states. The result of that is they do have to release some energy to do so. And that is was referred to as being sort of exothermic for the atom. It will give off that energy to allow the electrons to come back down to whatever energy level they sort of end up with. As the energy is either being absorbed or even really being released, a lot of times it's released as sort of a photon of light with a specific wavelength. So I think we finished up last time sort of talking about waves and some different aspects of waves. First off, as you can see there, the wavelength with its lambda is really the distance between obviously two peaks or two troughs there. We also have the amplitude, which is sort of from the midline distance to the top here. We also talked about the frequency, which is new here. And the frequency is basically how many times per second a wave sort of passes through a particular point. Remember that the frequency has units of 1 over seconds or reciprocal seconds. Also, a reciprocal second is also a hertz. So that's also a very common unit of frequency, and they are basically the same thing. So a reciprocal second is basically the same as a hertz. Interchanged in terms of the units associated with it. One sort of aspect that we look at is sort of the speed of a wave, which is a lot of times given in meters per second. So a lot of times when we're dealing with waves, in terms of wavelengths, meters is a very common unit that we use a lot. Centimeters and nanometers are also very common units that we use for wave. Reminder again that there are 100 centimeters in 1 meter. And in 1 nanometer, there are 10 to the minus 9 meters, or 1 times 10 to the minus 9 meters is equal to 1 nanometer. Again, that flip around the wrong way and go 10 to the minus 9 nanometers meters. So that again is the proper way to do it. And it is like 1 times 10 to the minus 9. So we're just going to pick up here where we kind of left off, I think, and continue talking about radiation and energy. And we talked about sort of energy being moved through space in the form of these waves. And again, there is a relationship between sort of the wavelength and the energy associated with it, and the frequency. So I think we might have talked about it last time, but if we have a very short wavelength, a high frequency, and that usually is a high energy sort of wave. And again, that's something like we're just going to go, if we have longer wavelengths and a lower frequency, that is usually lower in energy. So there is sort of a relationship between the wavelength that's coming off for a photon of light and sort of the energy associated with it. Electromagnetic radiation can be characterized as sort of waves and also particles. So we talked, I think, about it as well. It's on the dual nature of light. So there's wave and particle type of relationships that occur. So something like electrons, which is what we're focusing in on this chapter, which is a particle, as we'll talk about a little bit later on, can have wave-like function and sort of behave like waves. And waves can also be sort of particle-like functions as well, with a wave or a photon light just being like a stream of particles sort of happening as well. So one can think of, like I said, a beam of light is traveling through space as these sort of packets of energy. We also talked about the idea of, as energy is either absorbed or sort of given off, is this idea of quantized sort of energy, where again, we talked about the idea is essentially that, you know, an electron, for example, will gain or lose enough energy to fully make the transition from one energy level to the next. They won't find themselves halfway between energy levels or anything like that. So they really do sort of gain and lose energy and whole number ratios that allow them to fully make those transitions. And the idea of quantized energy, as we talked about, is the idea kind of like stairs, as we'll see shortly. Again, either you're on one level or the next level. You never really find yourself sort of in between stairs or anything like that. And that's sort of how electrons transition. And as I mentioned, the longer the wavelength of light, the lower the energy and the lower the frequency, and the higher energy, shorter wavelength, much higher energy associated with those type of come off. See here, even with colors, for example, and we do see colors like in the flame tests, when the wavelength of light that's coming off is in the visible part of the spectrum, where we see colors like red, orange, yellow, blue, green, indigo, and violet. And even with colors, there's a difference in terms of energy. As you can see here, the red wavelength is a lot longer than the blue wavelength here. So our wavelength for red is here, our wavelength for blue is here. So red has a longer wavelength than blue, and we would expect red then to have actually lower energy than the blue, as blue has a shorter wavelength, a higher frequency. So sort of the red part of the spectrum where we see color, red, orange, and that part is kind of the lower energy in terms of colors. And kind of the blue, violet, that part of the sort of color spectrum where we see colors is going to be more high energy because of their wavelength are lower. Now, one sort of aspect of waves as they move is basically the speed at which they move. And that is 3 times 10 to the 8 meters per second, or 186,000 miles per second. That is actually a constant, and that is the speed of light, which is c. And that is a number you should know because it does pop up a lot. 3 times 10 to the 8 meters per second. And we could actually use this equation here to help us calculate one of two things. If we know the frequency, we could figure out the wavelength associated with that wave of light, or vice versa. If we know the wavelength, we could figure out the frequency associated with it, and they both equal the speed of light when you times them together. So that is the speed of light is equal to the wavelength times the frequency. Once again, if we put our units in here, it is meters for the wavelength, it is 1/seconds for our frequency, and our speed of light ends up being units of meters per second. So it's really important when you use this equation that the wavelength is in meters, so everything cancels out correctly. We could rearrange it, and it's the same rearranging no matter what you're solving for. So the wavelength is c divided by the frequency, or the frequency is c divided by the wavelength. So those are two rearrangings of that equation. The good news is they're both basically the same calculation. You definitely want to make sure that you use your exponent button, obviously, in a situation like this, so that everything comes out correctly. Why don't we try one here and see? Why don't we do... Let's do, what is the wavelength in nanometers associated with a wave that has a frequency of, we'll do 5.6 times 10 to the 14 reciprocal seconds. Here. Okay, let's take a look. So again, we use really the same equation here, regardless if we have the wavelength or the frequency given to us. In this case, we do have the frequency given to us, and we're looking for the wavelength. So we're going to divide this to the other side, and that will give us the wavelength is c divided by the frequency. In this case, c is our constant, which is our speed of light, which is 3 times 10 to the 8 meters per second, divided by our frequency of 5.6 times 10 to the 14 reciprocal seconds. We want to make sure definitely that we use our exponent button here. So that's 3 exponent button 8 divided by 5.6 exponent button 14. That's going to give me, we'll call it 5.4 times 10 to the minus 7. The units here are going to be seconds, and seconds are going to cancel. Going to leave us with meters plus u that is left over at this point. Once again, we wanted nanometers here, so we'll take our conversion, which in this case would mean 1 nanometer is 10 to the minus 9 meters. Again, not the other way around. Doing a little dimensional analysis here, we'll go with a 1 nanometer up on top, 10 to the minus 9 meters on the bottom, so that they cancel. Once again, that basically is 1 times 10 to the minus 9. So we'll divide by that, and that's going to get us about 540 nanometers in this particular case. Any questions on that there? So again, really important, exponent button, when you put it in there, that you get the right answer. If you find yourself just off on the exponent part, it is probably how you're putting it into your calculator. Any questions on that calculation there? Okay. So depending on sort of, as for example, when electrons transition from one energy level to the next, they will give off that energy in the form of a photon. And really depending on sort of the wavelength associated with that photon that's coming off, it may fall in some different parts of what's known as the electromagnetic spectrum. And there's different sort of parts of the spectrum. On the right-hand side, in this particular picture here, we have a longer wavelength, as we talked about here. That would mean a lower frequency and a lower energy associated with it. On the left-hand side, we have a much smaller wavelength. That would mean a higher frequency and it also means higher energy. So as we go through the electromagnetic spectrum here, first off, down in this region here, we have radio waves. Again, kind of a longer wavelength, lower in energy, which is why it's not too bad when we listen to the radio and all that in our car. Next to it, we have microwaves, a little shorter of a wavelength, also increases the energy. Again, able to kind of spin water molecules really fast in your food and cook your pizza in like 3 minutes. So you're all good on that. Going to the left are microwaves, we have infrared, which again, the wavelength's getting smaller, a little bit more higher in energy, sort of where we feel heat and stuff coming off. Next to the infrared region is the visible part of the spectrum. That is where we see colors. Once again, that is our Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet type colors. And as I mentioned before, there is again a difference in terms of the energy. Around 700 nanometers, we got red, which is going to be lower in energy because it has a longer wavelength than, say, over here at the violet side or purple side. About 400 nanometers, we have a much higher energy as the wavelength is smaller. So even within colors, as I mentioned, there is sort of a difference in energy. So red, orange, yellow, kind of on the lower end, and then into our blues and our sort of violets is kind of higher in energy in terms of the visible part of the spectrum. Continuing past the visible part of the spectrum is their UV. Like we used, I think, UV boxes the other day in lab, right? You turn it on, had the UV light. Why we put sunblock on as well, so we don't get too burnt as we walk outside from the UV radiation, as it's high energy, so it kind of blocks it a little bit. To the left of that, again, shorter wavelength happening here. We got X-rays. Obviously, again, why they give you the lead vest and step out of the room when they shoot the X-rays. It's pretty high in energy. And at the very end of the spectrum there, we have gamma rays, which is basically just pure energy. It's a radioactive sort of particle like alpha, beta. And then there's gamma, alpha being positively charged particles, beta being negatively charged particles, and gamma rays basically having no charge. So kind of like a neutral sort of species, just really high energy. So as we go from right to left on this particular picture here, we're increasing the energy. You do need to know this electromagnetic spectrum. You don't need to know the exact where everything comes off at. You put it in order from like highest energy to lowest energy, shorter wavelength to longer wavelength, higher frequency, lower frequency. That also includes the colors. You need to be able to put the colors in order the same way, high energy, low energy, wavelengths, and so forth. So as we were talking, again, these guys will give off and absorb these sort of packets of energy as they transfer from one place to the next in terms of the energy level. And there is a way that we could calculate the energy associated with a wave coming off by really knowing one of two things, either the frequency or the actual wavelength. So this energy on the bottom there is, or this formula on the bottom is the energy is equal to H times V. H is a constant. H is Planck's constant, which is this number right here. And that is a constant number like the speed of light, which is the 3 times 10 to the 8. And this again is our frequency. So if we look at the energy associated, or the units associated with this, H is joules times seconds. So that's what those units are. Joules is an energy unit. Obviously, seconds is a time. And if we times it by our frequency, which is 1 over seconds, the seconds will cancel. And when we use this equation, we will end up with units of joules when it's all said and done, which is good because that's a unit of energy. We can obviously calculate the energy associated with a wave if we know the frequency. We could also tie this equation in with the one that we just saw earlier and just used, which is our C is equal to the wavelength times the frequency, where the frequency is equal to C divided by the wavelength. So we basically could take that whole thing and put it right in for the frequency. And we get another sort of very useful version of this equation, which is the energy is equal to H times C divided by the wavelength. So H and C are constants. So that's your speed of light and your Planck's constant and the wavelength. So this is how, if you just know the wavelength, you could plug it in there and figure out the energy associated with it. Or if you just know the frequency, you can plug it into the original one there, the H times the frequency, and figure out the energy associated with it. Once again, we do want to be careful on units. And for our wavelength here, in this equation here, it does need to be in meters because the speed of light's in meters. So everything will cancel out correctly. So those are two ways you can figure out the energy associated with a particular wave that has a wavelength or a frequency. Any questions on that there? So why don't we try the one we just did there? Let's calculate the energy associated with what we just calculated, which I think was, what do we have there? 4 or something? At 540. Okay. So I want you to calculate the energy in joules associated with a wave that has a wavelength of 540 nanometers. And again, our nano being 10 to the minus 9. Okay, we're going to calculate the energy, which is H times the frequency. Using our substituted version there, we could substitute in HC divided by the wavelength. And again, that comes from this relationship that we saw earlier, that the frequency is C divided by the wavelength. So we're basically just substituting that into here to get to there. Again, the top numbers here are all constants. So that's going to be our Planck's constant, which is the 6.63 times 10 to the minus 34 joules times seconds. Our speed of light, 3 times 10 to the 8 meters per second, divided by our wavelength. Once again, though, we do need to get it into meters. Otherwise, we're going to be off because we're in nanometers here. So we'll do our conversion here to take it back to meters, which I think we had earlier. And again, a nanometer in this case would be 10 to the minus 9 meters. Those guys are going to cancel and give us like 5.4 times 10 to the minus 7 meters, which would go here, 5.4 times 10 to the minus 7 meters. In terms of units, the meters on top and bottom will cancel. Seconds will cancel, going to leave us just joules that are left. And if we do that, once again, making sure to use our exponent button, 6.63 times 10 to the minus 34 times 3 exponent 8 divided by 5.4 to the minus 7, going to give us an energy associated with that guy about 3.7 times 10 to the minus 19 joules. Questions on that calculation there? Now, just to show you that, I think in the original question we had back here, we had the actual frequency given to us. So we could have just used the frequency if we actually had the frequency also given to us, and just put it into this equation, and just to show you that you should get the same answer here. And putting the frequency in just the way it was, which was 5.6, I believe. 5.6 times 10 to the 14 reciprocal seconds, and seconds cancel. And at that point, you will end up with, should be the same number, 3.7 to the 19. So again, as you can see, all you would need is the frequency, or all you would need is the wavelength, and you could calculate the energy associated with that wave, regardless of which one you have. Any questions on either of those calculations there? Okay, so you should know how to do those calculations, obviously, there. Talk about that. All right, so as we've been talking about, what we're really talking about a lot in this chapter is really those electrons transitioning. And Bohr's theory of the hydrogen atom, as we'll talk about here a little bit, is what's sometimes referred to as the planetary sort of model, where there's sort of a nucleus in the middle and there's these nice orbits, and electrons are basically moving around sort of in these circular patterns. As we'll talk about, it's not really how they move, but this is sort of the Bohr's model. And he basically thought of electrons as either being restricted in a certain orbit. It's either in like this orbit here, which is like the n equals 1 orbit, n equals 2, n equals 3 orbits here. n equals 1, n equals 2, n equals 3. These are basically the energy levels, with n equals 1 being closest to the nucleus, n equals 2, and so forth being further away. So we envision sort of these electrons moving around in these nice circular patterns. And as the electrons sort of transitioned, say from a higher energy level to a lower energy level, it would have to give off that energy in the form of a wave that has a particular wavelength associated with it. And what it would do as a result of that is it would give off some type of emission. An emission spectrum is given off as electrons from a higher energy to a lower energy level, because the atom is basically emitting off the energy to allow those electrons to do so. The result of that is, for example, that it looks like a spectroscope with a prism in it. You may be able to distinguish colors coming off, distinct lines of colors coming off as a result of the photons of light that are coming off. Now, spectrum are the spectrum by sort of elements are more of what are referred to as a line spectrum. And the difference between sort of a continuous spectrum and a line spectrum, as we'll talk about, is really sort of the energy that's happening there. So, few ways to put it in a fire like you did, use an electrical disk. It's going to excite all the electrons and stuff like that. Spectrum is one where, like the sun, for example, everything sort of comes off at once. So you have wavelengths of light coming off at all sort of areas along the way. For example, when we see something that's red hot, obviously the glow is part of the visible part of the spectrum where we can kind of see colors and stuff glowing. We also could feel the heat coming off, which will be part of the infrared sort of region of the electromagnetic spectrum. So not all electron transitions, for example, will result in energy be coming off in the visible part of the spectrum where we actually see colors and stuff like that. Could come off really anywhere along that spectrum that we saw. Could be in the UV part, could be in the IR part, could be in other parts where you wouldn't necessarily see colors. Like fireworks, we do see colors, right? When you shoot off fireworks, you explode, right? With some explosion, which gives off a lot of heat and energy to the elements that are in the fireworks, excites their electrons, and those guys give off energy in the form of visible light that we go, oh, green color, pretty, blue color, right? Purple colors and stuff like that comes off. So a common feature, though, of the sun and heated solids is that you have this sort of continuous spectrum that comes off. And if you remember, we talked a little bit about quantized energy and the idea that it's like stairs. You can kind of think of a continuous spectrum, kind of like a ramp that you're walking up. And literally on a ramp, right, you could pretty much lay it up anywhere, right? You could stop at any point along the way. You don't have to be at a certain level. And that allows everything in terms of wavelengths to come off at once. This is what you kind of see with the sun, like a rainbow type of effect, like everything coming off basically all at once. And that's different than how elements are. They are more quantized, which means you're either there, or there. As we talked about, if you're walking upstairs, you're not going to stop halfway through. You're either going to have enough energy to go from this level to that level. And the result of that is when we heat elements, especially in the gas phase, we see more of what's referred to as a line spectrum. And because they has to be on this level, or they has to be on this level, or the transition from one level to the next has to be complete, we end up getting these very distinct lines that occur if you look at it through a prism like a spectroscope. And they obviously occur at different colors, not just that color, but they occur at different colors and different wavelengths. And elements, so spectrum, particular element, and based on the lines that you see, at, it has its own sort of unique spectrum as to what lines you see kind of highlight as the electrons are transmitting. Here is the emission spectrum for hydrogen. So like hydrogen in its gas phase, again, if you do an electrical current through it or do something to it, it will give off these sort of 4 distinct sort of colors at these wavelengths. And as you can see, they are lines. So there's specific one. And each of these little lines represent a transition of an electron in hydrogen from one energy level down to the next. So that is what we're seeing here, this sort of quantized transition that occurs. And for example, we have like a red, right, versus over here, which is more of a purple or violet color. And earlier we talked about energy here, right, between, say, these two colors. The one that is lower in energy would be which one? It'd be the red, right? This would be a little bit higher in energy. So what we're talking about is we have these electrons at these different energy levels, say n equals 1, n equals 2, n equals 3, n equals 4, and so forth. And let's say we had an electron that was on the 4th energy level and it decided it wanted to come all the way down to the 1st energy level versus that was maybe in the 3rd energy level and decided it wanted to come down just energy level. And my made up example here, which we'll use hydrogen's lines here for our question, that's obviously not hydrogen's exact transitions, but the one that went from the 4th energy level all the way down to the 1st energy level, would it be represented, do you think, by the line on the left or the line on the right? We'll start with, if I went from the 4th energy level all the way down to the 1st, does that take a lot of energy to do or not a lot? It would be a lot of energy, right? It's like, if you want to think about the stair example, you walk down 4 stairs basically, right? So a lot of energy to come down the 4 stairs. That should be a lot of energy, which means the wavelength should be long or short? Short, right? And in terms of colors and short colors here, it would be more the violet one here, right, in our example, as opposed to my electron that went from the 3rd energy level to just the 2nd, right? That's like going down just 1 step, right? Not a lot of energy needed to go down 1 step, which means it'll be lower in energy, right? Which means the wavelength should be longer, right? And in this made up example here, that would probably maybe correspond to the red color we see. So each of these are basically a result of these electrons transitioning. You can make a fairly good guess just based on the colors that you see and their positions as to sort of maybe how far that electron is maybe transitioning. Obviously, it's moving a lot of different energy levels. It's going to require the atom to give off that amount of energy, right? A good amount of energy for those electrons to come down. That would result in a lower wavelength in terms of the wave coming off, as opposed to just an electron making a smaller transition, which would allow the atom to release a lower amount of energy, and that would have a longer wavelength associated with it. Any questions on that there? So Bohr's model of the atom, as I mentioned, is this sort of planetary model where he thought basically, again, electrons were sort of transitioning around the nucleus in these orbits. Again, they're restricted to sort of these orbits, and they can only transition from one energy level to the next. It works really well with hydrogen, which actually only has 1 electron, but his theory sort of falls apart as you get multiple electrons sort of involved. And when you get multiple electrons involved, you have a lot of electron and electron repulsions that occur because electrons are negatively charged. So it doesn't work very well for all things past hydrogen. Let's sort of describe like we sort of the lines of those electrons from one energy level basically to the next. Again, the idea here is that they are in those fixed orbits about the nucleus. And as an electron would transition down to a lower energy level, again, the atom would give off that in a form of a wavelength, which, as we just talked about, you could calculate the energy associated with that by using our equation there that we just did an example of, if you know the frequency or even if you know the wavelength, as we did in that calculation. Here's a prettier picture of that. And again, each of those lines resulting from those electrons being dropped down from a higher energy level to a lower energy level. Speaking of energy levels, that is what is sometimes referred to as quantum number, or the principal quantum number. And it is the n number, and n is the principal quantum number. And it can have values of 1 through 7, where n equals 1 is the ground state. And anything kind of above that, 2 through 7, are referred to as excited states. The ground state is closer to the nucleus. Anything above that is getting further from the nucleus. So n equals 2, 3, 4, 5. And we're getting farther and farther away from the nucleus. Quantum number, yeah. Yeah, it would be the lowest energy level. In the case of Bohr, it would be like the first little orbit right around the nucleus. N equals 2 would be the next one, third one. Even again, they don't really work in orbit. To Bohr, in general, we talk about as being sort of the lowest energy level, closest to the nucleus. So those are electrons on that first energy level are really kind of right there next to the nucleus. And then you kind of build out away from it. As we'll talk about, they really don't travel in pretty circles, but they're still traveling randomly in that empty space around the nucleus. And the sort of their distance from that nucleus is sort of the n equals 1, n equals 2, and so forth. Other questions? Quantum numbers, there's really 4 different types of quantum numbers that you'll talk about when you get into 1A, but we're just going to kind of stick with that for now. We'll talk a little bit about it maybe next time as well. So as I mentioned before, those 4 lines that we see is really a result of those electrons transitioning. And once again, this little guy here that just went 1 sort of transition there in the middle would probably result in a lower energy, longer wavelength than our guy here that went from here all the way down, basically to the bottom, which will give us a shorter. This is the idea of quantized energy and continuous energy. Again, all the way through, all kinds of wavelengths happening. Where electrons will be are transfer from one energy to the next level. There's our staircase, for example. So Bohrs model, as I mentioned, worked really well to describe what's happening with electrons and their transitions in hydrogen. But further experimentation and even sort of theories that came out after that basically kind of moved us away from the idea of Bohrs model of this sort of planetary model and orbits. And like the idea of orbits is, you know, the electrons going around in a circle, which means I can put my finger there and eventually, right, it's going to come back around and it should be there, which means we have a pretty good idea how it's moving, where it will be. If we just wait long enough, it'll come back around the circle and stuff like that. A lot of experiments and theories, starting with de Broglie here, came up with the idea that particles like electrons will have wave-like functions, and they really don't sort of travel in these nice pretty orbits and nice pretty circles and stuff like that. So de Broglie's idea, which was actually just an idea, he actually didn't do any experiments, he just came up with it. People later did experiments and said, sounds about right. He came up with the idea that, you know, particles, for example, like electrons, could behave like wave functions. And he came up with this idea of sort of like the standing wave. And it's like a guitar string. If you pluck a guitar string, right, you'll see the wave, but really, obviously, it can't go anywhere because it's like attached to the guitar, right? So the string is not going to pop off or anything like that. And that's sort of the idea here with a particle like our electron, where there is obviously going to be some attractive force between the electron, which is negatively charged, and the nucleus, which is positively charged. And it will be able to have this sort of wave-like function where it's really tied to the atom through its attractive force to the nucleus, kind of like the string on the guitar, but it can still move and vibrate around like the guitar string could move around, and the electron could vibrate and move around in that empty space outside the nucleus. But it is still sort of restricted in sort of where it can move around. There's also in a wave places where there's no amplitude, and those are what he referred to as nodes. And those are sort of places where it gets really kind of close to the nucleus. So some points along the string were called nodes. They do not have any amplitude. These nodes at each end, and there may be nodes in the beginning, in the middle as well, between the ends, again, like if your string was on the guitar there. Basically, the idea here was he reasoned that waves can behave like particles, And again, particles can exhibit wave-like functions, which is really moving us away from Bohr's model of the orbits and these nice pretty circles at which they are moving. A really big sort of move away from Bohr's idea came with Heisenberg and Heisenberg's uncertainty principle, which basically says it's impossible to know simultaneously both the momentum and the position of a particle with any type of certainty. So the idea of Heisenberg is the more you know about the momentum, the less you know about the position of a particle, and vice versa. The more you know about sort of the position of a particle, the less you know about how it's moving. And that's basically totally different than Bohr's idea of, well, I know they're in circles, they keep moving around this way, so I definitely know where they should be and how they're moving. To this idea that we really don't know how a particle like an electron is moving. It is moving really randomly about the nucleus in some type of pattern. So we're moving away from the idea of orbits. That we could do is this idea of what are referred to as orbitals. And this is based on what is referred to as Schrodinger's equations, which is a bunch of calculus type equations. And if you ever take physical chemistry, you'll do all those equations. Save it to the end. Everybody says physical chemistry to the end. But the idea that sort of came out of this is the transition from Bohr's model of orbits to, like, I know for sure is traveling a pretty circle, to this more wave mechanical model of, I think electrons are in what are referred to as atomic orbitals. And what are atomic orbitals? Atomic orbitals are essentially probability maps, where you say, I think it's a pretty high probability that I can find an electron here in the atom. I'm not really sure how it's there, where it got there, how it's moving, but I think there's a reasonably high probability that in this atom I could find an electron in this location. Now, the high probability to find an electron would probably be near the nucleus, again, because of the opposite charge. And as you sort of fan out from the nucleus, the probability of finding an electron does start to decrease. When we talk about atomic orbitals, as we'll talk about here, there's a few different types. There are s orbitals, p orbitals, d orbitals, and f orbitals. And these are all atomic orbitals. They are essentially based on Schrodinger's equations, probability density maps of within an atom. This is a pretty high probability of finding an electron there. You know, like if you went to a driving range for golf, there's a high probability of finding a golf ball on the grass in front of the driving range, right? So could be like right in front, could have a whole bunch in front, could have some just shanked off to the right in the parking lot. Hopefully a less of a probability if you shake it into the parking lot, maybe not, I don't know, depending on your golf game. But you know, there's a lower probability that if you park your car, it's not gonna get hit by the golf ball based on its location, right? So that's sort of the idea with electrons. I know we've all put it in the parking lot once or twice, maybe more than twice. So this is sort of the idea of a probability map for electrons. And obviously the darker area is a higher probability of finding an electron. Lower, kind of lighter area, less of a probability. Nucleus is kind of thought of being kind of there. So you can see kind of dark. And as we sort of travel some distance out from our nucleus, we see the probability starts to decline. Does it mean we can't find an electron there? No, it just means there's probably a less of a probability of finding an electron there than, you know, closer to the nucleus. Again, like my bad golf example, higher probability of finding the golf ball in the grass than say in the parking lot, right? But there's still a good probability that you might find a golf ball in the parking lot as you walk through it. Hopefully not near your car, I would hope, yeah. So that's the same idea. Much like my golf ball example, not sure how that golf ball got to the parking lot, right? Nobody knows how it got there. Nobody knows the route it took. It just happened to end up there, right? It's not the guy running away really quickly with his golf clubs holding on to him. So let's talk a little bit about these atomic orbitals. There are different types of atomic orbitals, and the first type is an s orbital. And s orbitals are spheres. So they're basically circles, and we do find s orbitals on every energy level. So Starting with the first energy level, which is our n equals 1, which is closest to the nucleus, we have what is referred to as a 1s orbital there. When we go to the second energy level, we have what is referred to as a 2s orbital. We go to the third energy level, we have a 3s orbital, and so forth. So on every single energy level that we have, there is always an s orbital. The first number where it says 1s, 2s, 3s, that is the principal quantum number. That is the energy level at which that orbital is at. So a 1s orbital is on the first energy level, and it's an s orbital. A 2s orbital is on the second energy level. It's also an s orbital. They are the same shape, but they do get larger as you go up energy levels to accommodate more electrons. So the circle kind of gets bigger and bigger to house more electrons in it. One really important thing about orbitals, be it a s orbital, p orbital, d orbital, f orbital, all individual orbitals could hold a maximum of 2 electrons. So no matter what orbital it is, an s orbital, p orbital, d orbital, if you have an individual orbital, it can only hold a maximum of 2 electrons in it. So here's a picture of an s orbital. Here's sort of the density diagram, and they kind of close the circle to get us to here. And again, it basically is this shape, and it just increases with size as we go up energy levels to accommodate more electrons. Once again, these are really theoretical probability maps. Are you going to find a circle or a figure 8 in an atom? Probably not. But these are, again, sort of these mathematical probability maps of finding electrons in an atom. The next type of orbitals appear on the second energy level, and they are what are referred to as p orbitals. And unlike s orbitals, there's actually 3 different types of p orbitals. There's a px, a py, and a pz orbital. And that's like in math. There's an x, y, and z axis, and there basically is one on the x, one on the y, and one on the z in 3-dimensional space. Basically, a p orbital, figure 8, or teardrop sort of shape, with kind of like the nucleus being thought of as being about there, and the high probability of an electron kind of in this area of the lobes there of our orbital. Now, the p orbitals do not appear until the second energy level. So on the first energy level, there is just the 1s orbital. On the second energy level, there's the 2s orbital. And this is where we start to see the 2 p orbitals appear. It is made up of 3 individual p orbitals, the px, py, and pz orbital. If I take all 3 of those orbitals together, if I take all 3 of these orbitals together, how many total electrons could I put in there? I could put 6. I could put 6 electrons, and these 3 p orbitals all together is what is sometimes referred to as a subshell or sublevel, depending on your book. So the 2p subshell, which is composed of 3 individual p orbitals, px, py, and pz orbital, could hold a maximum of 6 electrons. Basically, if each of those lines are the orbitals, 2 electrons in each, basically. An individual 2p orbital could hold how many electrons? Still only 2, an individual p orbital, right? So individual 2p orbital can hold 2. The 2p subshell, which is all 3 of them together, 2 times 3 is a 6 total electrons that could happen there. The next type of orbitals that are important appear on the third energy level. And by the way, this is what the p orbitals look like. They are figure 8s, and here's our density map again with sort of the nucleus being there. You see the highest density of electron probability sort of near that nucleus at that point. Z in terms of 3-dimensional space. The next important orbitals are d orbitals, 5 different d orbitals. And the d orbitals do not appear until the 3rd energy level. So once again, on the 1st energy level, we have our 1s. I'll go up here. We have our 2s, our 2p. And then on the 3rd energy level, we have a 3s, a 3p, and this is where our 3 d orbitals first start to appear. All 5 of those 3d orbitals is a 3d subshell. Our level, our sublevel. If I max out the d subshell, how many electrons can I put in there? 10, right? 2 in each, and there's 5 of them. So we can put a maximum of 10 electrons in that 3D or any D subshell that we have, 3D, 4D, or so forth. The next important orbitals is actually the F orbitals. Not sure where that slide went, but we'll throw it in here. F orbitals, there are 7 different types of F orbitals, and they start on the 4th energy level. So once again, on the 1st or 1s, on the 2nd, 2s, 2p, on the 3rd, 3s, 3p, 3d, and on the 4th is where we start to see 4s, 4p, 4d, and 1, 2, 3, 4, 5, 6, and 7. I'll squeeze it in there. Or 4f. And once again, that would be the 4f subshell that could hold a maximum of 14 electrons if we filled up every single orbital in there. Single orbital in there, you do not. To max it out, you would have to 14 in there. Electrons go into the atom, lowest energy first, and then continue to fill next lowest, and next lowest until all the electrons basically be distributed. We talked about the subshell. If we take, for example, something like the n equals 3 here. On the n equals 3 level, that is what is referred to as a level or a shell. If I want to max out the electrons on the n equals 3 level, how many electrons could I put in there? Well, the n equals 3 level would be everything in the red box. That would be this guy, which you call 2, 4, 6, 8, 10, 12, 14, 16, and 18 electrons if you filled up everybody on that level. How about the n equals 2 level? How many electrons in there? It would be 8. The n equals 2 would be everybody on that 2nd energy level, which would be 2, 4, 6, and 8 electrons if we fill them all up. Nobody wants to draw all this, so there's a quick way you could calculate maximum number of electrons on a level. It is 2 times n squared, n is the energy level. So if you did the one we just did before, n equals 3, 3 squared is 9, 9 times 2 is 18. 2nd energy level, 2 squared is 4, 4 times 2 is 8. So you want to do the squaring part first and then multiply by 2, and I'll give you how many electrons. So if I was on the 6th energy level, how many electrons could I put in there? 6 squared is 36 times 2 is 72. 72 electrons, yeah. So I can put in there. Any questions on that there? Okay. So let's talk a little bit about the energy of these electrons. Because they go in basically one at a time, lowest energy to next lowest energy. When we're dealing with hydrogen that has only 1 electron, what we see is the energy of all these orbitals, they're equal to each other. What I mean by that is everybody on the 2nd energy level here is all equal to each other in energy. Everybody on the 3rd energy level here is all equal to each other. When we start putting more and more electrons into the atom, we run into a little problem of electrons are negatively charged and there's more electrons which are negatively charged. Do they really want to be near each other? The answer is no, they really don't. But because they're kind of tied to the nucleus, right, they can't leave in most cases. So they have to kind of move around and spread around. And it does affect the energy of the individual orbitals and the order at which they go in. So when we get more than one electron, we see this kind of shift in the order of these orbitals. And the major shift happens right around here. It goes like you would imagine, 1s, then 2s, then 2p, then 3s, 3p. After 3p, it actually goes to the 4s orbitals first. They actually end up being lower in energy. Then it goes to the 3d, and that pattern happens up here, 5s first, then into the 4d. So it's really important to know the correct order at which electrons go into the atom so that you can write electron configuration. If you know the correct order and you know that S's could hold 2 electrons, P subshell 6, D subshell 10, F subshell 14, you'll be able to write any electron you want. This is actually the order at which electrons go into the atom. We always start up here. And we basically follow the arrow to the end, and then we zigzag back around and follow the arrow to the end, and we continue that pattern. Here again, the S at maximum of 2, P subshell 6, D subshell 10, F subshell 14. It's also really important to remember, as we talked about, that on the first energy level, there's just S's. On the second energy level, that's when P's occur. On the third energy level, that's when D's occur. And on the fourth energy level, that's when F's occur. Because if you remember that, you frankly can recreate this yourself on the paper by going first energy level 1s, second energy level P's, third energy level D's, fourth energy level F's. And pretty much all you have to do is just fill in the numbers underneath each of these. So this would be like 2s, 3s, 4s, 5s, 6s, 7s. This would then be 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, and 5f. And really quickly on the piece of paper, you could basically recreate that for yourself. All you have to remember is 1, 2, 3, 4. Just put the numbers down underneath there. Any questions on that there? So if you know those two things, like I said, you really can write any type of electron configuration you need to. So let's talk about writing electron configuration and what it is. Electron configuration tells us how the electrons are distributed in the atom, what orbitals they are in, what energy levels they are on. If we are dealing with something that is neutral, then the atomic number, which is the number of protons, as we talked about, will also tell us the number of electrons there are. And we could basically do that and write our electron configuration accordingly. So let's take a look here. Why don't we start with number 1, which is hydrogen. Hydrogen's atomic number is 1, which means if it is neutral, it has 1 electron and it should have 1 proton. So 1 electron is important. We would start at the very top of our little chart there, and we would go with 1s1 is how that is worded, would be the electron configuration for hydrogen. The 1s1 is written like that, big 1, little s, and superscript 1, maybe not that big. First one is the energy level, the principal quantum number. So that's on the first energy level. The S tells us we're hanging out in the s orbital on that energy level. And the superscript 1 is how many electrons there are in that particular energy orbital or subshell. There's no dashes, there's no commas. It's just 1s1 is how you write it. Another way that we could represent electron configuration is what is referred to as orbital diagram. And in an orbital diagram, you use boxes or lines to represent the orbitals, and you use arrows to represent the electrons. So if we were to draw the orbital diagram here for hydrogen, we would show 1 electron And always the first electron that goes into the orbital will have this sort of arrow pointing upwards. It actually represents what is known as the spin quantum number, which is ms. And it has a +1/2 is usually denoted like that. There are actually 4 quantum numbers. We don't get into too much of it here, but we saw n, which is really our energy level. There's L, which is really the orbital that the electrons are in. M sub L is how many of the orbitals there are. And really, the real definition is actually the orientation in 3-dimensional space, like a px, a py, and a pz type of orbital. And m sub s is the spin quantum number, which could be +1/2, which means the arrow points up, or it could be -1/2, which means the arrow points down. So I mentioned the 4 quantum numbers because it's actually important for what we're going to talk about next, which is what do we do with the next electron? So in this s orbital, we could put one more electron in there before it's filled. And there's really a couple of options you could do. You could either put it in going in the same direction, or you could put the electron going in the opposite direction. And there actually is a rule that we follow, which is known as Pauli's exclusion rule. And Pauli's exclusion rule basically says that no 2 electrons in the same orbital can have the same 4 quantum numbers. So you may be saying, how are they different? So how they're different is if we take our helium, or we don't take helium, but we take helium, which is number 2 on the periodic table, its electron configuration would be 1s2 basically. So we're going to fill up that s orbital. We already with hydrogen took our 1s orbital and we put our electron upwards. Now, as I mentioned, we could take our next electron and go up and up, or we could take our next electron, go up and put the next one down, basically. So what makes it different here is this. If we were to do the 4 quantum numbers for this particular electron here, which is this electron, and also this electron. Not that you need to know how to do this at this point, but let me just tell you what the 4 numbers would be. N would equal 1, L would equal 0, M sub L would equal 0, and M sub S would equal +1/2. So these are what are referred to as the 4 quantum numbers for basically our electron pointing upwards in this case. Now, clearly, if I decided I wanted to put my next electron like this, that is pointing the exact same way in the exact same orbital, which means it will end up with the exact same 4 quantum numbers. And that is what Pauli's exclusion rule says is a violation and cannot occur. So because they would actually end up with the same 4 quantum numbers, we cannot put our next electron pointing in the same direction. Now, is it really different, this guy here that's pointing downward? Well, if we were to do this guy's numbers here, this guy's numbers would be, if I get something right with here, there we go. This guy's number would be n is equal to 1, which looks the same. Its L would equal 0, which looks the same. Its M sub L would be 0, which kind of looks the same. But now the spin here is not pointing upwards, which is +1/2. It's actually pointing downwards, which is considered -1/2, which is the major difference between those two. And by putting the electron sort of pointing downward in terms of a spin, electrons have their own spin affected by magnetic electrical field. It does not violate Pauli's exclusion rule because now both of those electrons, a slim difference that it is, it's just a spin, is different. They now have different quantum numbers, both of them, and they do not violate Pauli's exclusion rule. And that would be the correct way to do it for something like helium, where it would be 1s2. We would put our first electron in upwards, and then our second electron goes downward. That basically tells us they have different quantum numbers, and that will not violate Pauli's exclusion rule. So for us at this point, that's all you have to remember: one up, one down, same orbital, first one up, second one down. This arrangement where we basically have opposite spins on our electrons is what is referred to as being paired spin. They kind of cancel each other up, one plus half, one minus half. They sort of cancel out their effectiveness on the atom by being paired off like that. Any questions on that there? So continuing on here to number 3 on the periodic table, that is lithium, which would be 1s2. We no longer have any more room in that box as we saw. We then need a zigzag back, and the next orbital you would go to would be the 2s orbital, and we would go with 2s1 in this case. This means on the first energy level, how many electrons do I have? I have 2 on the first. On the second energy level, I have 1. Yeah. So I have 1 electron on a higher energy level, and I have 2 electrons on a lower energy level. And if we were to do our orbital diagram, we would need 2 boxes. One represents the 1s orbital, one represents the 2s orbital. And by the way, I'm just going to go to the right. Truthfully, if you did this correctly, you would go up in terms of energy, right, to show the energy difference between them. But I will run out of room, obviously, on my page, so I'm just going to go to the right. But normally, you know, you would have like, if you properly did it with the right energy, it would look, you know, like this, right? The 1s, and then the 2s is higher in energy and so forth. First one goes in, second one goes down, next one goes up. Yeah, we can now see we have room for 1 more electron there in our 2s orbital before we would have to move on. So if we do that, let's go to number 4, which is beryllium. Be 1s2, 2s2. At this point, we now have 2 electrons in the second energy level, both hanging out in the s orbital. We have 2 electrons in the first energy level, also hanging out in an s orbital. Our orbital diagram here would be something that looks like this: up, and then down in terms of that. At this point, we've now filled up our 2s orbital. Now, electrons would have to go into what orbital after that? After 2s, if you follow the little zigzag, we come back, it comes to 2p next. So that would be the 2p orbital. And to show you that, that is going to be boron, would be 1s2, 2s2, 2p1. In this particular case, how many electrons are in my second energy level? It is 3, all 3 of these. 2 here and 1 here gives me 3 electrons in the second energy level. And we obviously have 2 electrons here in the first energy level. In this case, we would actually need 3 boxes for our p orbitals. This would represent the px orbital, the py orbital, the pz orbital. And it would go up, down, and the very first one in the p subshell here will go up in the far left there. And at this point, how many more electrons can I put in that 2p subshell before it's filled? Give it 5 more, right, before it fills out. We now run into another important aspect of this, which is, where do I go with my next electron, right? I have a couple of options. I could, with my next electron in that 2p, end up pairing it off. I could not pair it off and go next door. And there actually is a rule that tells you which way you should do it, and it is not this way. The rule that tells us what we should do is what is referred to as Hund's rule. And Hund's rule basically says that the most stable arrangement of orbitals is one that maximizes parallel spins. So if you remember, we saw earlier that if we put electrons going in opposite directions, this is what is referred to as paired spins. Electrons all heading in the same direction is what is referred to as parallel spins. So what we would do is, basically, when you run into a p subshell which has multiple individual orbitals, a d subshell which has 5 individual orbitals, or an f subshell 7 individual orbitals, we always fill the orbitals like this. When there are multiple ones in the subshell, we always do one at a time, left to right, and then we come back when we have no other options and start pairing off. So one at a time across until we run out of room, and then come back and pair off is how we would do that. So when we get to something like carbon, for example, which is 6, it would be 1s2, 2s2, 2p2. And we would have our orbital diagram here, 1 up, 1 down, 1 up, 1 down, 1 up, and now our next one would go right next door into the py orbital. The pz orbital will then get 1, and then we'll come back and start pairing everybody off. So those two aspects of sort of how you draw your orbital diagram are important. 2 electrons in the same orbital should always be paired, opposite spins. When you have a subshell that has multiple individual orbitals, everybody gets 1 at a time going in the upwards direction. That maximizes the parallel spin and then comes back basically and pairs it off. Any questions on that there? All right, nitrogen. So once again, nitrogen's atomic number is 7, which means it has 7 protons, and would also again have 7 electrons in a neutral atom. So if we wrote the electron configuration here for nitrogen, we would start with 1s2. Again, we would zigzag back on our little chart. It would take us to 2s2, zigzagging back there, would then take us to 2p3. Remember that when we sort of write the configuration, it should look like that: 1s2, 2s2, 2p3. Once again, there's no commas, no dashes or anything like that when you write the electron configuration. You just lay it out like we just wrote it. In addition, remember that the first number there is the energy level. So basically what this 1 here represents is the n equals 1 level. So on the very first energy level, we basically have 2 electrons in the s orbital. This guy would be on the second energy level. So would that guy. So those guys would both be on the second energy level, a little further away from the nucleus. And we have 2 electrons in the s orbitals, and we have 3 electrons there in the p orbital, which means we have a grand total of 5 electrons on the second energy level and 2 electrons on the first energy level. Once again, if we did our sort of orbital diagram, we'd have our appropriate boxes. And again, we're not really drawing this properly in terms of energy, but just to save space, we'll go across, bless you. And again, here we would continue to fill our electrons 1 at a time in the upwards direction, which represents positive half of spin in terms of the electrons. At this point, we can see a couple things looking at the p subshell there. We basically will now have to start pairing people up as we come in with our next electron. And we also have room for 3 total more electrons before that p subshell is filled. Any questions on that one there? All right, so we might as well finish out the first 10 here. So we'll go to oxygen next, continuing on with the configuration. 1s2, 2s2, 2p4. Once again here, filling in our orbital diagram, up and down, paired off, up and down, paired. Again, going 1 at a time in the upwards direction. Now that 4th electron will come back to the first box there, our first orbital, and we will pair it off in that first orbital, which in this case would be the px orbital. Now we can see we have basically 2 spots left until we fill it up. So again, we'll continue down to fluorine, which is number 9 on the periodic table. And fluorine, which is 9, would end up with 1s2, 2s2, 2p5. So we're almost there to fill the subshell. And our orbital diagram will look pretty much like oxygen, except that we'll have an extra electron pairing up. So once again, up and down, up and down, up, down, and down here. Once again, leaving our last sort of p orbital available. And obviously that will happen when we go one more over on the periodic table to neon, which is 10. And that will basically fill up our 2p subshell. So let's take a look at that one there. So at neon, we end up with a configuration of 1s2, 2s2, 2p6. And again, at that point, we have now filled in the last electron in that subshell. So up, 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 and then down, down, and down. At this point, if we do have more electrons that we need to fill, we would have to continue down through our zigzag sort of chart there. And that should take you to the 3s orbital. Next would be where we would go. Any question on electron configuration, orbital diagram here? All right. So why don't you do Argon's configuration there? And while you're at it, why don't you do, yeah. Yeah, you can, the limit would be obviously the element. So, yeah, but yeah, so you go on pretty much, the 100 and whatever it is up there, technically speaking. So you do not obviously have to fill up all the orbitals with the electrons. You obviously would just fill what you need for that particular element. But yeah, it could kind of keep going, stuff like that. Other questions? All right, so why don't you do argon? Why don't you also do why not? Let us do, for the fun of it, let's do nickel as well. So nickel is I'm getting old, but I think it says 28 there. All right. If you want on this one, you can just write the electron configuration. You don't have to do the orbital diagram. So let's do the electron configuration for nickel and argon here. Okay, let's take a look and see. So we'll start with argon. So again, starting at the top of our chart, we should end up with 1s2. Then we got to go to 2s2, then to 2p6. Once again, here, if we count up the top numbers, they'll tell you how many electrons you already distributed. So 2 and 2 is 4, and 6 is 10. So we got 8 more to go. After the 2p, we're going to go to the 3s2. And that would now be 12 total electrons. After the 3s will come the 3p6, which once again, if we count up the top numbers there, we should end up with 18 in this case. In this case, we have 8 electrons on the third energy level, right? 2 in the s and 6 in the p. We also have 8 electrons on the second energy level, and we got 2 electrons on the first energy level. Any question on that configuration there? All right, so let's look at nickel, which is 28. So we'll take a look at nickel here. It would be 1s2, 2s2, 2p6. Once again, here we'll go 3s2, 3p6. And at that point, that is 18 still. Up next is, again, it is the 4s that comes first. So it will be 4s2. And then we zigzag back to our 3D subshell at that point. And we will end up with 3D8 in this case. We add up the top numbers there. Should equal 28, I hope. Yeah. Any question on that configuration? So again, that is a very common mistake people make. They gotta go to the 3D, then the 4s. Again, in terms of filling, the 4s orbitals are lower in energy than the Ds, so they will get those electrons first. Any question on any of those two? Yeah. Yeah. There was. So if we want to, we could steer real quick here. So if we take a look at it, we would have, and again, I'm just going to go sideways here for space saving. So we have our 2s, we would have our 3 boxes for our 2p. We would have our box here, our line for our 3s. We would have our 3p there. We would have our 4s. And then we would have our 3D here. And it basically would feel like this: one up, one down, one up, one down, up, 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 come back and pair, up and pair. Again, to the P, we would go one at a time, and then come back and pair. This would go up, this would go down. And then with the D, same thing would happen. We would go up first. So that's 1, 2, 3, 4, 5, 6, 7, and 8. So it looks something like that. Yeah. Other questions on that? Now, when we also look at these two sort of configurations together, the top one being obviously argon here, and the bottom one there being nickel. When we look at this part of nickel's configuration through here, that configuration is how many electrons? Is 18, which is essentially who on the periodic table here? It is basically argon's configuration, right? So that first little part there is basically argon's configuration. So there is sort of a shorthand that is sometimes used with electron configuration. Some people sometimes refer to as noble gas sort of configuration. And basically what we do is, because a part of, say, nickel's configuration is basically argon, you could shorthand it and go in brackets argon, which would represent the electron configuration for argon. And you would just continue on with the rest of the electron configuration there. And you would have argon, 4s2, 3d8 in this case. What goes in the bracket is always a noble gas. So it's always group 8. It's always the noble gas of group 8 that comes right before the element you're writing your electron configuration for. So for example, if we looked at magnesium, which is 12, 1s2, 2s2, 2p6, 3s2, there would be magnesium. If we take this part of magnesium, that is how many electrons? That is 10 electrons on the periodic table. 10 is neon. So we would put neon in little brackets and continue on. So that's sort of a shorthand for electron configuration. It is always the noble gas that comes right before the element that you are writing. Yes.
I did that for gold.
Very good. Yes. Yeah, you could do it for any of the elements, including the transition metals. It doesn't matter. You just basically back up to the noble gas that comes right before it, and you just kind of continue on with the configuration. Any questions on that there? All right. All right. Now, the idea of the off-ball principle is sort of based on the idea that protons are basically added to the atom one at a time, and we sort of add electrons really kind of the same way. They're added one at a time to the atomic orbitals. Again, lowest energy first, following really the couple of other important rules that we talked about last time. Again, Pauli's exclusion rule, which is the one where, again, if you have two electrons in the same orbital, they have to have different spins. So one up, one down, they're paired. And again, our Hund's rule, which says, as we just talked about, maximum stability there going well direction. So here's another example. This is potassium. Again, if we take the first part of potassium, we once again will have argon's configuration, which is 18, and we can continue past it with the 4s1s. You could write it either way, unless it explicitly tells you not to use the noble gases. But other than that, you could write electron configuration either way. Any questions on that there? Now, transition metals, which again are between group 2 and group 3 on the periodic table. They have incompletely filled d orbitals. They also give rise to cations, which incompletely filled d orbitals. There is actually, well, there's actually several exceptions to the electron configuration in the transition metal region. There's a lot of exceptions that if you follow sort of the zigzag sort of method there, you'll actually get maybe the incorrect electron configuration. But for our class, we're just going to worry about two notable exceptions, which most people sort of think about. And that happens in the first row transition metals, and that is copper and chromium. Chromium being 24 and copper being 29. And for example, if you do chromium's a configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. This is what you would get if you followed our zigzag sort of method here. And chromium, along with copper, has been found to be experimentally more stable with actually an extra electron up in the d orbital and one less electron in the s orbital. So basically the exception is one of these electrons basically come up over into the d orbital. And it also happens there with copper as well. So chromium's configuration, if you shorthanded it, would be argon 4s1, 3d5, and copper would have the exact same sort of exception, except that it would then fill up all of the d orbitals with electrons and have 3d10. It's able to do this really because the 4s orbitals, for example, and the 3d orbitals are really, really close in energy. So they're very, very close in energy, and it doesn't take a lot of energy for that electron to kind of pop up into the higher energy level. What actually happens when we start actually filling the d orbitals with electrons is they actually end up switching in energy. So what actually happens is the electrons go into the 4s first because it's lower in energy. And then as you actually start populating the d orbitals with electrons, these two guys actually end up switching in terms of energy. And you actually end up with the 4s electrons being higher in energy than the 3d electrons. And this is why sometimes you will see electron configuration written like an order. They'll write it like 3s2, 3p6, 3d4, and kind of put them all in order. And that is electron configuration written based on energy rather than filling. And just so we're clear, in this class and pretty much every chemistry class you take, you write electron configuration based on filling, how they go into the atom, which means the s's come first and then the d's. I've only took one class in my whole life where they wanted you to write it the other way. But in reality, what does happen is it does switch. Those energy of those orbitals do actually switch. Where that's going to be important is, as we'll talk about here, when they start losing electrons. So when transition metals start losing electrons, they actually lose different electrons because there's this switch in energy. But when the electrons go in, and how you should write the electron configuration, again, is the filling order, which is the S should get it first and then the D. Now, for us, chromium and copper are the two exceptions that you need to know. Just so you know for real, if you go under chromium and copper on the periodic table to like silver and underneath, and then kind of in between those two, there's a lot of more of these type of exceptions where there's extra electrons going up into the D. For example, PD has no electrons in its S. They've all went up to the D. So, you know, there's a lot of exceptions. Silver is an exception as well that has a similar type of situation occur. So usually chromium, copper below, and then kind of in between them. There's a lot of these exceptions. But for us, again, you're just responsible for chromium and copper. For anything else, you could write it following the zigzag thing. Just know in reality is probably incorrect for some of those in that region. Any questions on that there? Okay. And again, they see chromium and copper exception at the end. So the lanthanide and actinide series, which are our guys on the bottom, that is our place where we do start to get into our F subshells. 4F for the lanthanides, 5F for the actinide series. And again, they give rise to completely or incompletely filled F subshells. Now, when we look at the periodic table, you could actually count off electron configuration using the periodic table. The first two groups, group 1 and group 2, that is what is referred to as the S block. That's because S has how many electrons? 2, 1 and 2, basically. Yeah. From group 3 to 8, that is what is referred to as the P block on the periodic table. And that's because P subshell can hold 6 electrons, which would be 1, 2, 3, 4, 5, and 6, basically. The transition metals is our D block on the periodic table. And that is because you could hold 10, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. The 2 rows, which are not on this picture here, that is our F block. The 2 rows at the bottom there, the lanthanide and actinide series, if you count across there, there's 14 boxes, which is the 14 electrons. So for example, the period numbers that we see on the periodic table, that's like our n equals 1, n equals 2, n equals 3 sort of number. So for example, if we were doing magnesium, which we did previously, we would start up here. And right here at hydrogen would be 1s1 to helium, which would be 1s2. This is now period number 2. This would now be 2s2. This would be 2p6 to the end. We're now in the 3rd period here. This will now be 3s2. So you could actually count it off if you like. You could go down to, say, calcium, which would then continue. This would then be 3p6. And then this is now 4s2 is a calcium. So you could count off electron configuration from the periodic table, but you do have to kind of understand a couple of important things. One important thing is d orbitals start on what energy level? D orbitals start on 3rd energy level. And this guy right here, even though he's on the 4th level here on the periodic table, is actually 3D. This guy would be 4D. This guy would be 5D. And this guy would be 6D. So that's the difference. You got to watch out there. And also, the Ds are 1 behind the period number. Our lanthanides and actinide series here should technically go up there at period 6. But this is F. So the Fs are actually 2 behind the period number. So it gets a little crazy down in that region. But if you pay attention and understand that, we could go down to our nickel we just did. So we had our 1s2, our 2s2, 2p6, 3s2, 3p6, 4s2. And literally at this point, you could go 3D 1, 2, 3, 4, 5, 6, 7, and 8. And just count out the boxes and you can get your electron configuration. Any questions on that there? I clearly was 1 slide short of that lecture, but here it is. There's our apps there. There we go. I was just ahead of it, I guess. So here's our 4F and our 5F, which again does go here. So these guys are 2 behind the period number. The D is 1 behind the period number as well. I personally would recommend doing the zigzag guy that we made earlier, because there are little places here where you can if you sort of count incorrectly, but you can use it in a quick way or to check yourself if you want, or if you feel comfortable doing it, you can do that as well. Now, let's talk a little bit about, go this way, I think. What happens when things do get charges? So let's say we had our magnesium that we did earlier, which was 12. Now, if magnesium made a +2 charge, how many electrons would it have? It would have 10 electrons in this case, right? +2 means it lost 2 electrons. So its configuration would be 1s2, 2s2, 2p6. And that is 10 electrons, which is who on the periodic table? Is neon's configuration. So magnesium, when it loses its 2 electrons, will end up at neon's configuration. If we took, say, nitrogen, which we did earlier, 1s2, 2s2, 2p3 would give us nitrogen. If nitrogen ends up with a -3 charge, it will then have 10 electrons as well, right? It goes 7 + 3. It would then have a configuration of 1s2, 2s2, 2p6, or again, neon. So all 3 of those things in this example, magnesium with a +2, nitrogen with a -3, and neon all have the same electron configuration. That is what is referred to as being isoelectronic with each other. So something that has the same electron configuration but are different things are referred to as being isoelectronic with each other. That is the basis of bonding, pretty much. Ionic bonding. The metals lose electrons, and what they end up doing is backing up to the noble gas that came right before them. And nonmetals in an ionic compound will gain electrons and go forward to the noble gas that comes right after them. So if you look on the periodic table, after nitrogen is neon is the noble gas, so it ends up there. And if you look behind magnesium, it is also neon. And that is the basis of all bonding, as we'll talk about, is everybody wants to end up with the same electron configuration as the noble gases because they're incredibly stable. And just so we're clear, something is isoelectronic, it doesn't become that element. It has the same electron configuration as that element, same number of electrons, still has the same protons to keep it as magnesium and stuff like that. But it ends up being the same number of electrons, which makes it really stable. And that's the purpose of all bonding, as we'll talk about, ionic bonding, covalent bonding. The purpose of it is everybody to get to basically the noble gas electron configuration because it's really, really stable. Yes.
I made some predictions as to what electrons for undiscovered elements on my paper.
That's good. We'll take a look at those later. Now, when we talk about transition metals, as we talked about a little bit earlier, they are a little bit different when they do lose electrons. So if we look at, say, iron, for example, which is 26, I believe. If we write the electron configuration for iron, which is 26, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 1, 2, 3, 4, 5, 6, 3d6. Now, when iron makes a +2 charge, it will actually end up with 24 electrons as it lost 2 electrons. Now, this is where we were talking about a minute ago about the orbitals of the 4s and the 3d, that the 4s is lower in energy, but then there's sort of that switch in energy that occurs when we start filling in the d electrons. So in the case of the 4s here, our 3d, this is again how it feels, but once we start doing that, we do get that switch in energy that occurs. And what ends up happening, as I mentioned, is the 4s actually ends up being higher in energy. And the 3d ends up being lower in energy. So what happens when things lose electrons is they typically will lose the highest energy electrons first. And that is because technically they are further away from the nucleus and not held as tightly. So those are the ones that go. So with transition metals, what will happen is because there's this sort of switch in terms of the energy of those orbitals, they will always lose the s electrons first. So in this particular case, when iron would go to lose electrons, it would actually lose these 4s electrons first, and it would lose both of them in this case. And that would leave us a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6 argon 3d6. Now, if iron actually went to a +3 charge, it would end up with 20, bad math there, 23 electrons. So what happens in this particular case is the same thing's going to happen. We're going to lose those s electrons first. Still need to lose actually one more. So what will happen is we will actually take out these electrons here, and then we got to dip into the D's next and take out the third electron. So we then would have to take out an electron from the D, and we would end up with a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and 3d5 are argon 3d5. So transition metals are a little bit different than representative sort of metals. Representative metals will, group 2 and group 3, they'll pretty much lose the last electrons in the configuration. Transition metals will always lose the s electrons first, and then if they need more, they will go into the d orbitals and start plucking out some d electrons. Any questions on that? Yeah. Yeah, so again, we write the electron configuration in the filling order, which would be what we have up there on top for the iron, that the 4s should get the electrons first, and then the 3d get them. And that's because, again, the 4s is lower in energy than the 3d. But what happens once that d starts to get populated is they actually start switching around. So you can kind of think of it at the end, once they're all kind of filled, there's like that shift that happens with the energy of those orbitals being higher in energy. So at that point, when it goes to lose an electron, it's actually going to lose those 4s because they actually end up being higher in energy once we start filling up those d orbitals. They go in first, but then they are lost first as well. So a good way to remember it, I guess. And it's only with the transition metals. So all transition metals, I think we had that picture a second ago. Actually, here, let's go this way. What's here, I think. There's that thing. Right here. So all transition metals, which are pretty much here, right? So these are all the transition metals here. When they do go lose electrons, these guys here will lose these guys first. These guys here will lose these guys first, and so forth all the way down. So they'll always lose those s electrons first, and then dig into the d if necessary. So why don't we try one like we did when we do nickel with a +4 charge? What would be the electron configuration? Nickel, again, with no charge was 28, I think we did earlier. Okay, let's take a look. So once again, we'll look back at nickel with, again, no charge was our argon 4s2 3d8. Nickel now with a +4 charge means that it basically has lost 4 electrons from this guy. And it should end up with 24 electrons when it's all said and done. So once again, nickel, which is a transition metal, and even though, again, our electron configuration has the s coming first, It is at this point higher in energy, so we will lose the 2 electrons out of here, which leaves us still 2 more to lose, and those extra 2 will then come out of the D, and it would give us a configuration of, we kind of use the shorthand here, argon 3d6. Any questions on that there? Which again would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d9, 3d6 at that point. Any questions on things with charges and electron configuration? All right, so talking a little bit about valence electrons. Valence electrons are really the highest energy level electrons. They are actually the important electrons in terms of bonding because they're further away from the nucleus. They're held this tightly, and that allows them to either be lost or shared easily. And they are the ones in the highest energy level. So again, if we look at the configuration here of nitrogen, which is 1s2, 2s2, 2p3, on our second energy level here, we basically have 2 and 3, which would be 5 valence electrons here for nitrogen. The other electrons that are there are sometimes referred to as core electrons. So these would be our valence electrons. And these guys here would be our core electrons, which are obviously closer to the nucleus and held really tightly because they're sitting next to that positive charge. So it's going to hold them really tight, and they're not involved in bonding. So the valence electrons are always involved in bonding. Core electrons are not involved in bonding. And it's also the reason, as we'll talk about, why certain things make certain charges. And that's why they typically will only lose their valence electrons when they do make charges. Now, you could write the electron configuration for everything, but nobody really wants to do that if you are looking for how many valence electrons there are. So the number of valence electrons for anybody actually equals the group number. So everybody in group 1 has 1 valence electron. Everybody in group 2 has 2 valence electrons. Group 3, which is boron, 3, 4, 5, 6, 7, 8. So if we look at nitrogen, nitrogen is group 5. So that is how come it has 5 valence electrons, is those that we just highlighted. If we look at carbon, it would actually have 4 valence electrons. Oxygen would have 6. And our noble gases there would have 8 valence electrons, except for helium. Yeah. Helium actually has how many total electrons? 2. So it can't have 8 valence electrons if it only has 2, right? So outside of that, everybody else there in group 8 has 8 valence electrons. Helium has obviously 2. And again, you could go with the group number as basically equal to the number of valence electrons, a much, much quicker way to figure out number of valence electrons, which is important for bonding. So let's talk a little bit about some periodic trends as we go through this. We talked a little bit about when we did the lab, I think the other day, metals and non-metals. As you go down a group, especially in group 1, they tend to give up their electrons a lot easier. So in order of losing electrons most easily, cesium versus rubidium, potassium, sodium, and lithium. This is again because they are further away from the nucleus. They're not held as tightly. And I believe that is what we saw in that video we were looking at, right? Lithium reacted, then sodium reacted more, then potassium reacted a lot more. So what we saw, right, is as you went down the group, there's a lot more reactivity occurring. That's because as you go down a group, they're easily giving away their electrons, which is going to initiate a reaction occurring. Most active nonmetals are found on the upper right of the periodic table. And that is also what we saw in the experiment, right? Going up the halogens, except for our Dudek test tube, we saw that iodine was less reactive than bromine. Bromine was more reactive than iodine, and chlorine was more reactive than bromine. And obviously fluorine would be more reactive as well. So as we talked about, going up for our nonmetals, more reactivity, going down on the other way there for our metals, more reactivity for our metals. And that is because as we go up for our nonmetals, we'll talk about it, but they have a lot of properties where they pretty much want to gain electrons, take people's electrons, which is going to sort of initiate a reaction to occur as well. So speaking of one sort of trend on the periodic table, which is really important, that is what is referred to as ionization energy. And ionization energy is the energy that's required to remove an electron from the gas phase of an atom. It is essentially how we make a cation, right? When we lose an electron, it becomes positively charged. Metals have relatively low ionization energy, and nonmetals have very high ionization energy. Electrons actually do come off one at a time. So even though we think of the thing that's losing 2 electrons, they don't actually come off both electrons at once. So if we did something like magnesium, for example, that we've been talking about, the first thing that would happen again is magnesium would dump 1 electron, and we would write that like this, where the electron's on the product side of the arrow. What next would happen is magnesium with a +1 charge would then lose 1 more electron, become a +2. And, you know, perhaps it would then maybe lose another one, and so forth. So the electrons do come off basically one at a time. And there's an ionization energy associated with each of the electrons that come off. This would be the first ionization energy. This would be referred to as the second ionization energy. And this would be, for example, like the third ionization energy. If you had to guess, is it harder to remove the first electron or the second electron? It is harder to remove the second electron. What happens with the size of the atom when you lose an electron? Does it get larger? Does it get smaller? Does it stay the same? When you lose an electron, you lost some of your electron cloud, so everybody kind of moves in, right? And when all these electrons then move in, they are now finding themselves closer to the nucleus, right? Which means they're going to be held tighter, and it's going to be harder to remove another electron. And when you do remove another electron, they're going to come in even more, right? Making it harder to remove the next electron. So what we see here is the first ionization energy, not too bad. The second ionization energy increases as you take off the second electron, and the third ionization energy increases even more as you try to rip off the third electron as well. So the general trend between, say, first ionization energy, second, and third is it increases as you go, you know, keep on plucking off electrons. So what about magnesium here? If we look at its configuration of 1s2, 2s2, 2p6, 3s2, why does magnesium, for example, only make a +2 charge? So what happens is after we rip off the first electron, right? By the way, magnesium here would have how many valence electrons? It would be 2. It's group 2, and it would be these guys right here, right? So these are core electrons at this point here. These are valence electrons. So as we rip off the first one, not too bad. That's a valence electron, not really held too tightly. Gets a little bit harder to take off the second one. But now when we come to, say, the third one here, what electrons are we into? We are into electrons, which started out pretty close to the nucleus and held very tightly, and now is finding themselves, after 2 electrons have lost, even closer to the nucleus and going to be held even tighter. And in the case of magnesium, it doesn't happen. It's like a almost like a 10-fold increase in energy if you wanted to do it, you know, between the second electron and the third electron, and it just doesn't normally happen and stuff like that. So that's why certain things will only form sort of fixed charges or certain charges. So things in group 2, after you get rid of the second electron, you're kind of into the core electron. So that's why they kind of stop at a +2 charge and only form a +2 charge. And things in group 1, for example, after you remove the first electron, you have a giant jump in terms of It's like, again, 10 to 12 times as much energy to try to remove that second electron. Something like sodium will always be +1 in that particular case. So that's the general trend of first ionization energy, second ionization energy, and third, and so forth. But in general, first ionization energy increases as you go up and to the right on the periodic table. So as you go this way, it increases, and it decreases as you go this way. If I have a very high ionization energy, does that mean it is harder to remove an electron? If I have a higher ionization energy, it is harder to remove an electron because that's the energy needed to remove an electron. So if you have a really big number, it's very hard to remove an electron. It probably won't happen. If you have a very low ionization energy, that means that's a lot of those electrons basically to be removed. You don't need a lot of energy to do so. Any questions on that there? Now, this also relates to a couple other things, which is atomic size. The size of an atom actually gets smaller as you go up and to the right, and it gets larger as you go left and down. And that is because as you go up and to the right, there's something known as effective nuclear charge, which is basically the positive charge that the electrons feel from the nucleus. It gets larger as you go up and to the right of the periodic table. So everybody's brought in a lot closer to each other. So you have a lot more protons happening on this side, makes it a bigger positive charge going to pull those electrons in, which means the overall size of the atom gets smaller. A little less happening here in terms of effective nuclear charge as well. So they don't pull those electrons in as far. So the overall size is a little bit larger as you go to the left. So a couple other important trends that we should talk about here is electron affinity. So electron affinity is the energy change that occurs when an element gains an electron. And on the periodic table, it basically increases as you go to the right in general and decreases as you go down. It's not a perfect trend, but that is sort of the general trend that happens. If you have an affinity for something, it means you like it, right? So electron affinity basically would be somebody that likes to gain electrons. And as you go up to the right, that is what occurs. And you go down to the left, it has a low electron affinity. That is basically what happens when we make an anion. Somebody becomes negatively charged, right? Another important sort of trend is what is known as electronegativity, which is different than electron affinity. Electronegativity is the ability of an atom to bring electrons towards itself. It also increases as you go up and to the right on the periodic table, with our good friend fluorine being the most electronegative element you could have. And it decreases as you go down. We also talked about the size of a cation, which is positively charged, gets smaller, right? Because it loses electrons. What happens when somebody gains electrons? The size of the ion now becomes larger, right? It gains some electrons, so the electron cloud gets larger than its neutral counterpart. So these are some important trends on the periodic table, and let's kind of maybe put them all together here to talk about them. So if we draw a big periodic table, also known as a big box, I suppose. As we go basically up and to the right, the size gets smaller and gets larger or increases as we go down. As we go up and to the right, the ionization energy, which is the energy to remove an electron, increases. And as we come down, it decreases. As we go up and to the right, electronegativity, which is the ability to bring an electron towards an atom, increases. and decreases as you go down, and electron affinity, which is basically the energy change when somebody gains an electron, increases as you go up and to the right on the periodic table, and decreases as you go down. So when we take all these sort of periodic trends together, as we go up and to the right of the periodic table, we have things that are really small in terms of overall size, which means the outer electrons are really close to the nucleus and going to be held tighter. And then we see that because it takes a lot more ionization energy to remove an electron. And they have a high electron affinity, which means they like electrons. And they have high electronegativity, which means they like their own electrons, but they also want your electrons as well. And all those things is what we associate with nonmetals. Nonmetals, again, because of their size, are going to hold their electrons a lot closer. They are also going to want to bring electrons towards themselves because of their high electronegativity, and also because of their high electron affinity, they want to gain electrons. They also do not really want to lose electrons because they have a high ionization energy. So all those things lead to nonmetals becoming negatively charged and anions because they are gaining electrons. And that is the opposite sort of trend that we see when we actually look out to the left of the periodic table, and specifically bottom left of the periodic table. As we go to the left and down on the periodic table, what we end up with are elements that are larger in size, which means their outer electrons are further away from the nucleus and not held as tightly. We see that by the very low ionization energy that they have, which means that you don't need a lot of energy to remove those electrons. We also see that they have very low electron affinity, which means they don't really like to gain electrons. They also have low electronegativity, which means they're not looking to bring electrons towards themselves. So as we go to the left and to the bottom left of the periodic table, we have elements that essentially are going to give up their electrons really easily. And when they do that, they will become positively charged ions, which are known as cations, because they have now released their electrons and now have more protons than electrons, hence the positive charge. So to recap here, top right of the periodic table, that is where we find our elements that basically will gain electrons, become negatively charged, and anions. And those again typically are your nonmetals. Bottom left of the periodic table are ones that typically will release their electrons, or give away their electrons, or lose electrons, and become positively charged and known as cations, and those are typically metals that do that. That should conclude chapter 11. Thank you very much for watching this recorded lecture. Have a good day.